I'll take a look at these homework problems. Let's see.
All right.
Okay, so this first problem was just a redo because we missed this in the previous set. If you remember earlier, you had changed the OH into a positive charge, but it should only become neutral because it started off negative. So we got that correct. So let's look at number 2.
Okay.
You'll have to scroll to the right so I can see your answer. Nucleophile donates electrons to join an electrophile. Base donates electrons to steal a proton. Electrophile receives electrons to join in a nucleophile. Acid receives electrons to lose a proton. Leaving group to leave something. Okay, that's very good. Also, I noticed that you kind of grouped these into 2 groups. Nucleophile together with base. They're similar because they both donate electrons. And electrophile together with acid together with leaving group. They're similar because they all receive electrons. That's a good way to learn these. So one thing that we've seen is difficult then is the things that make something a good nucleophile often can make something a good base as well. So it can be sometimes difficult to tell what role something is going to play. That's one of the challenges in organic chemistry. And sometimes it might be difficult to tell whether something's going to be an electrophile or an acid, although usually that's more straightforward. There's more clear rules for that. Okay, yeah. Very good. So, okay, great. So we can take a look at number 3. H3O plus and hydroxide are examples of acids and bases. Okay, good. We talked about how that's useful to remember that acids want to receive electrons because H3O plus is positive. And OH minus wants to donate electrons, so bases want to donate electrons. Do you know, what's the name of the OH minus ion?
Hydroxide, did you say?
That's right, hydroxide. I let the cat out of the bag. That's right. And what's the name of the H3O plus ion?
Not sure.
So that is hydronium. We might not have mentioned that before, but that's a real important species. So that's good to have written down. H3O plus is hydronium. Okay.
Okay.
Number 4, an atom with a negative formal charge could be a nucleophile or a base. So sometimes it can be difficult to tell which one it's going to be. An atom with a positive formal charge is going to be an acid or a leaving group, except if the positive charge is on a carbon, it would be an electrophile. Okay, number 6, identify whether... so that would have been a better thing to write there. You might have said, instead of saying maybe electrophile, you could have said it's an electrophile if the positive charge is on a carbon. That way we can be more specific. We don't really have to guess in that case. All right, number 6. Okay, yes, so NH2 would be a base. What makes it a reasonable base?
Lone pair.
That's right. Now we talked about how you might think this would be acidic because there is a delta positive charge on the hydrogen, but it's actually a pretty small delta positive charge, so you're not going to really see many examples in OChem where this acts like an acid. So base is a good answer. Good.
Okay.
So your answer was a good one. Number 7, how can you identify strong acids? Positive charge or... All right, so that's an excellent answer. That's exactly what I was going for number 7. That's exactly right. Things with positive charges are strong acids. Anything with a positive charge is a strong acid, or the 4 neutral strong acids. That was very good. How can you identify strong bases? O minus, N minus, C minus. Let's see, what was that last thing off to the right? Alkyl lithium. Excellent. Yeah. All right, that's exactly what I was going for too. It's a little bit harder to identify the strong bases, but that's what you have written down there is basically what you need to have memorized. So that's good. Chloride, bromide, and iodide. Number 9. Those are generally nucleophiles. Great. So the point is they're generally not bases. And remember we saw why. Hydrochloric acid is an extremely strong acid. So its conjugate would be not very, very weak base. So chloride is hardly basic at all. Good. So they're generally nucleophiles, not bases, even though they have negative charges. So what you wrote down was right. That was good. Number 10, oxygen. So you wrote down that the oxygen is kind of like a pseudo-leaving group. Okay, that's right. I wasn't thinking of that, but that is a good answer. But there is another role that we've seen the carbonyl oxygen playing in the recent reactions. We've seen it doing this a lot. What's the other role the carbonyl oxygen can play?
The role of base.
Strong base or weak base?
Weak.
That's right. Even though it's a weak base, though, it plays that role very frequently. So we should definitely make a note of that. I'm sure we'll see a bunch of examples of that in a few seconds when we look at the later problems in the set. So that's the main thing I was going for here. How about nucleophile? Is a carbonyl oxygen generally going to be a nucleophile?
No.
No. So I don't know if you remember, but we kind of discussed those issues in our last session. We saw even though a carbonyl oxygen has a lone pair, it generally does not play the role of nucleophile in an introductory course anyway. So we just kind of memorized that the carbonyl oxygen plays the role of a weak base, but not a nucleophile. Okay, you're right. It often also plays that role of this pseudo-leaving group. That's a good answer too, but it's very important. The key things I wanted to emphasize here were it's often a weak base, but it's generally not a nucleophile. Okay? Number 11. Excellent. So hydrogen sulfate is generally a spectator, even though it has a negative charge, because the negative charge is resonance stabilized. It's so resonance stabilized that it's completely unreactive, almost.
Okay.
All right, number 12. Acids make other molecules into better electrophiles and leaving groups. Perfect. That's exactly what I was thinking. They do that by giving the other molecule what type of charge?
Positive.
Yeah, the most important factor in organic chemistry is the charges. Acids make other things positive, which make them better electrophiles or leaving groups. So how do bases make other molecules into better nucleophiles? What type of charge do they give them?
Negative.
Good. So your answers were correct there for number 12. That's what I was going for. How can you make a molecule into a better electrophile? By adding an acid to it. So what I was going for was adding an acid. Good. How can you give a molecule a better leaving group? Add an acid. So that was right. How can you make a molecule a better nucleophile? Add a base. We're going to talk about that some more today, but those are the correct answers. That's what I was going for. Okay, so let's see. From that page, it looks like you got pretty much everything right. The one thing that you weren't quite on the same page as me was number 10. I wanted to review what we talked about last time. Carbonyl oxygens are weak bases, but not nucleophiles. We'll see that some more as we go on. But overall, that was those. You saw what I was going for on that page. That's good. Some of those questions were a little bit vague, but you had the answers I was thinking of. So that's good. Number 14. Okay, here we go. So number 14 is just a nucleophile-electrophile reaction, and then we're done. A simple one-step reaction. At the first one. Then the next one. First you did a nucleophile-electrophile reaction, then you did an acid-base reaction, and you used another molecule of NH3 to take the proton. That was good. Remember, the iodide is a very, very weak base, so it's better to use the NH3. Good. Excellent. Okay, so the next example. So the next three examples, I gave you a hint. First, the leaving group fell off. Then the nucleophile attacked. Okay, good. First, the leaving group falls off. Then good, thanks. Okay, good. And again, you're using another molecule of the alcohol here for the acid-base reaction in the last step. That is a good learning process. Good. All right, so the next example. Scroll a little bit to the left. Okay. Now, this next example, so now I'm looking at the example with the hydrochloric acid. Can you point to that so I know we're looking at the same example? Sure. Great. All right. So what role did the oxygen play in the first step?
Leaving group.
Now, is that oxygen a reasonable leaving group?
It doesn't look reasonable.
No. Are neutral oxygens generally acceptable leaving groups?
No.
No. So that looks like we've made a mistake there. So try to come up with an alternative first step. What does it look like should really happen first in that reaction? You may as well probably just yeah.
Okay.
What does it look like is going to happen first?
I was confused by that. It did, like it said, the next three reactions, the leaving group just falls off, and so I was kind of confused why that would have just fallen off. But
okay, good. So let's try to rethink that. So what would be a more reasonable first step?
For the oxygen to have acted as a base, to take the hydrogen from chlorine.
Good. In fact, that should be pretty much automatic, because remember, we've seen when there's a strong acid, you always start with an acid-base reaction. When there's a strong acid, you always start with an acid-base reaction. So try drawing those arrows. Let's see what happens when we do that.
Okay. I'm just going to erase this other stuff. Okay, so if we were to do that, we would...
Okay, so far so good. Does it look like we're done?
No, it doesn't.
So let's try to draw in the next step. Try to come up with some reasonable arrows for the next step.
Well, that would just give us the same thing. So looks like we did this instead.
Okay, so let's talk about that for a moment. So what type of reaction did you do first? Acid-base or nucleophile electrophile?
Base. Yeah.
You started with acid-base. So according to what we studied last time, what type of reaction should happen second?
Nucleophile electrophile.
That's right. So that's the pattern. Let's continue to talk about this for a second more before we continue. The other way you could see that what you written down there before was incorrect, I think you saw this, is that what you tried to do would not have made any changes. It would have kind of just reversed the first step. So that the acid-base reaction you were going to do was just going to move the proton from one alcohol to another, and you would get the same mixture of products either way. But you can just avoid that by remembering that we usually alternate from acid-base to nucleophile electrophile. Now, here's the point where I wanted you to use the hint up above for this second step.
Oh, I see. So it was in the next step.
So notice I didn't say the leaving group falls off in the first step.
Yeah, okay.
So that's what I meant when I said you slightly misinterpreted that.
I see that. Okay. So we actually just have a leaving group falling off right here. So that makes more sense.
Okay. So does it look like we're done?
Not quite. I think we will add more of this alcohol to act as an electrophile and nucleophile reaction.
That's certainly reasonable, but is there any better nucleophiles around?
Yeah, the chlorine.
Yeah. That looks like a better nucleophile, right, with a negative charge, so that would be a better reaction to use.
That makes sense.
The reaction you wrote was possible, but it wouldn't be the major path here. It's better to use the better nucleophile. Okay, does it look like we're done?
Yeah, it does.
Okay. By the way, note, I don't know if you remember, but what we have now is actually identical to what you had when you did this on your own, except for the first step. You just had the wrong first step, but these second steps are what I think they're what you had written down before anyway. Okay. So let's zoom out so we can take a look at this. This is a pretty common pattern in OChem. Okay, so we do have to always make sure our leaving group is acceptable. So the hint here was just maybe a little bit unclear. The leaving group, so on these problems, the leaving group does fall off, but that doesn't mean it falls off in the first step. I see you just somewhat misinterpreted that. Okay, now, So, did this reaction start with an acceptable leaving group? Did the alcohol start with an acceptable leaving group?
No, it did not.
What can you do to give something a better leaving group?
You can add an acid.
And that's exactly what we did here, isn't it?
Yeah.
The chemist added the acid. What was the purpose of the acid? How did that acid help the second step?
By making it more positive.
To give it a better leaving group. Good.
Yeah.
Okay. So that's one of the things I wanted to focus on today. How chemists add acids and bases to help their reactions. Because notice all of these reactions, I just drew the starting materials for you. But a lot of problems in organic chemistry, you have to come up with the starting materials yourself. So I want to start going over the thought process that you could use so you could see that you need an acid in this case. A chemist would say, gee, I'd like to do a reaction with alcohol, but the alcohol doesn't have a good leaving group, so I have to add the acid. So I think you're getting pretty good now at predicting the products if you're giving the starting materials. So we need to start going on to the harder problems where you start thinking of the starting materials yourself. So I'm trying to convince you that you could have realized on your own that this reaction needed an acid, even if I hadn't added it in there. That's one of the things I want to work on today. Okay, and you can see why the acid was important, because otherwise it wouldn't make sense for the leaving group to fall off. Okay, so you might that would be a good one to mark, since our first answer there was incorrect. Okay, so I'll take a look at the next example. Okay, so what role did you say the H- was playing here?
Nucleophile.
Okay, are there any other roles that seem plausible for H-?
Base.
Yeah. Now let me go to my screen. This is confusing, but actually H- is pretty much always a base.
Okay.
Let me go to my screen and try to summarize this. We actually summarized this last time, but it's a little confusing. And I told you not to worry. I actually told you not to worry about memorizing it, but maybe now's a good time to start memorizing it a little bit more. So.
Okay.
So bases are tricky. Remember that strong acids are pretty easy. Anytime you see a strong acid, you can expect it. You can expect to start with a acid-base reaction. But with bases, it's trickier. I guess we should start trying to memorize this. I told you it was complicated not to memorize it, but I guess we kind of should start trying to memorize this. You can work on this as part of your homework.
Okay.
So when you have these things, you always start with an acid-base step. These things always react as bases in an acid-base step at the start. These things will act as bases if there's an acid around. Otherwise, they're going to act as nucleophiles.
Okay.
And O- is just tricky. O- can either be an acid or a base. It depends on the exact details of the reaction. And so you just have to learn what O- does for every particular reaction. So O- is just tricky. It can go either way. You just have to memorize the details for particular reactions separately. So we're not going to worry about that too much right now.
Okay.
All right, that's a little bit complicated, but we'll try to clarify that as we go. So tell me when you have that in your notes.
Okay.
Okay.
So I guess
try to rethink this example that we were looking at.
All right. Okay.
Okay, so that looks better. All right, so that's another one to mark. Okay, so what role did the H minus play?
It played the role of base.
Good. Do you know what the name of that H minus ion is?
We said it.
That's called hydride.
Hydride.
So this is sodium hydride. And what role does sodium hydride play?
Base.
Always a base. This is pretty much always this is only used in OChem problems as a base, never as a nucleophile. Sodium hydride is always going to be a base, not a nucleophile. So how did the sodium hydride help this reaction? How did it help the second step?
It made something nucleophilic.
Made the oxygen more nucleophilic. Yeah. Now the oxygen was already nucleophilic. Even a neutral oxygen is nucleophilic, but it's not a very good nucleophile. So it took a poor nucleophile and made it an excellent nucleophile. Okay, so that's an important reaction. I think you've seen that there was a problem with the next reaction as well, so let's try redoing that one.
Okay. Yeah. Okay.
Let's see. Okay. Okay, right. So when you did this originally, you had the, what's the name of the H- ion?
Hydride.
Right. Originally, you had the hydride acting like a nucleophile, but now we've memorized what role does hydride always play?
Base.
Yeah. So, and then how did the hydride help this reaction?
It made oxygen nucleophilic.
More nucleophilic.
More nucleophile.
All right,
yeah.
good. So, okay. So let's take a look at your next example. You have to scroll to the right a little bit so I can see your full answer there. Maybe zoom out a bit. Okay. So it looks like you were a little bit puzzled by the answer that you got.
Yeah.
Because basically you kind of said that you got back to where you started.
Yeah.
Okay. And that does mean that probably we made a mistake somewhere along the way. So let's see. Let's take a look at the first step. Now, the first step is a no-brainer because anytime you have a strong acid, you know there's going to start with an acid-base reaction.
Sure. Yeah.
So what type of reaction was the first step? Acid-base or nucleophile electrophile?
Acid base.
So according to the pattern we studied last time, what type of reaction should the second step be?
Nucleophile, electrophile.
But what type of reaction did you draw?
Acid base.
That's why you just got back to where you started. You did one
Yeah.
acid-base reaction where the oxygen gained a proton. Then you did another acid-base reaction where it lost the proton. So obviously you would almost get back to just where you started. Now, actually, last time when we said that we usually alternated acid-base and nucleophile electrophile, I didn't explain why we did that. I just gave it to you as a pattern. But now you can kind of see why. Do you see that it doesn't really make sense to do two acid-base reactions in a row? Because if the first acid-base reaction adds the proton, if you just do another acid-base reaction right after that, you're just going to take the proton right off and get back to where you started. So you can kind of see why it makes sense to alternate. If you do two acid-base reactions in a row, you're just going to cancel out the first one with the second one. So now, hopefully, the pattern will be easier to remember if we now see why it actually makes sense. Okay. So we have to try again. What type of reaction should we probably be doing in the second step?
A nucleophile electrophile reaction.
So see if you can come up with a reasonable way to do that.
Wait.
Okay. What role is carbon-3 playing?
Electrophile.
And why is that reasonable?
It is attached to a positively charged atom like
Right.
oxygen.
So remember, the atom with the positive charge is probably not going to be the electrophile. At first, you were trying to make the oxygen the electrophile, but we've discussed that it's usually the attached atom that's the electrophile when something has a positive charge.
Yes.
What role is the oxygen on the right playing?
Nucleophile.
And why is that reasonable?
Lone pair electrons.
That's a good point. But there's somebody else here in the mix who's a better nucleophile.
Okay. Yeah. Bromine.
Okay, so that would be a much preferable reaction.
Yeah. It's funny. I think I'm mixing up roles because I know we had talked about how bromine negative charge will not be a base. So I think I'm tuning it out.
Yep, that's why it's important to do the practice, to diagnose those misconceptions. That's right. So it would be very easy to get confused about all of that. Is bromide a good base? Is bromide basic?
Extremely base.
Yeah, so really not a base because it's the conjugate of a strong acid. But is it a nucleophile?
Yes, it is.
A poor nucleophile or a good nucleophile?
Good nucleophile.
Really an excellent nucleophile. If you think about it, it's one of the most common nucleophiles, right? We've used halogens as nucleophiles in many reactions in the past.
Yeah.
Okay, but so this is where things get challenging because we've actually covered a lot of material so far, and ideas just start to get confused in people's minds. That's the purpose of doing these problems, to diagnose the confusions and try to iron them out. Okay, so let's try to continue here.
Okay.
Okay. All right. So what was going wrong here? So there were two lessons on this problem. One lesson was, if you start with an acid-base reaction, what type of reaction should you probably do next?
Nucleophile, electrophile.
Yeah, we talked about that pattern last time, but now you can see why it makes sense. If you just do two acid-base reactions in a row, the second one's probably just going to cancel the first one.
Yeah.
That's why you're... and also we've seen, try to pick out the best nucleophile in the mix. Actually, let's scroll back up to the earlier page of homework. Problem 9. What was your answer to problem 9?
Nucleophile.
But I think you kind of forgot that when you were doing the problems on the next page.
Yeah.
So that's important to emphasize. So what confused you? Well, we saw that chloride, bromide, and iodide are not basic. They're generally not. They should not be used as bases, even though they have negative charges. They generally should not be used as bases, even though they have negative charges, because they're so weak. But they are still excellent nucleophiles. Okay, I think that probably messed us up on a bunch of those questions, so we'll have to rethink those. Let's go on now to number 14. So we'll have to mark that last question. That was another one. There might be quite a few here. I think there was quite a few confusions coming up here, so there might be a lot to review on these. So let's look at the next. Okay. So how many steps did you do in the next reaction?
I only did one. But I mean, just based off of what we were talking about, I think that kind of.
Why should you have felt that you probably were not done with that just one step?
I had a positive charge.
Right, but you couldn't, because you had that misconception about the halogens, you couldn't think of a reasonable next step, so I can see what happened. Okay,
Yeah.
But that should have made us uncomfortable. All right, so now let's try to come up with a reasonable next step.
Yeah.
Okay, that looks much better.
So I did not finish this again, unfortunately.
Okay.
So I need to.
All right. Well, we'll get. So let's mark this question as one that again we got wrong originally. Now, what role did the HBr play in the first step?
The HBr played the role of acid.
That's
in the
right.
first step.
And how did that acid help this reaction?
It made the cyclohexane, I guess, more electrophilic.
That's right. It made it, because actually are alkenes electrophiles.
Alkenes are nucleophiles.
So are alkenes electrophiles?
Alkenes are not electrophiles.
But, so if we want it to get attacked by the bromide, we're going to have to treat it with an acid to make it electrophilic. So this is a good example of how an acid can take something that's not electrophilic at all and make it into a good electrophile.
I see, yeah.
So how can you make alkenes electrophilic?
By adding an acid.
Okay, now let's look at the next example. Let's see. Okay, so how many steps did you do in this next example?
I did two. I believe there needs to be one more step.
Yeah, why does it look like we're not done yet?
We still have a positive charge on the oxygen there.
Can you think of a reasonable next step?
We just did a nucleophile step, so we could likely do an acid base with water. And that would neutralize our main molecule. Like that.
Okay. So the thought process that you were talking through there was a very good thought process. That's the exact way to think about it. You said, I just did a nucleophile electrophile reaction, so now I need acid-base. That was a good thought process. And you used another water. Sometimes students don't like to use another water because they think that they used the water up in the previous step. But remember, there's many water molecules. Just because we used up one doesn't mean there's not billions more floating around, especially because that would probably be the solvent.
Yeah.
Okay, we don't use the hydrogen sulfate. We know the hydrogen sulfate is extremely unreactive because of the resonance stabilization.
Right.
Okay, so I guess we should mark that one as well. All right, so we had a bunch of these we had some difficulties with. So it looks like you might not have had too much time for this homework since you didn't finish it anyway. But so my advice for the homework is something that would have served you here would have been reviewing the tutoring notes more carefully before doing the homework problems. Or doing some homework problems and then re-reviewing the tutoring notes, because I think every single problem here is almost identical to one that we already did together in the last tutoring session. These were all just basically redos of the problems that we did in the last tutoring session. So if you had gone back and looked at that tutoring session, looked through that again, you might have cleared up some of your confusions. For example, you would have seen many examples in that last tutoring session where we used halogens as nucleophiles. So that could have reassured you that halogens really can be used as nucleophiles. That would have been one of the big things here. We also did some reactions with the sodium hydride, so that you could have studied those to see how sodium hydride reacts. Okay, so that would be my advice. My advice is I'm going to continue sending you homework exercises after each session, and my advice is before doing the homework exercises, read through your tutoring notes carefully. Then start working through the homework exercises. But then probably when you're in the middle of the homework exercises, you should probably go back and again browse through the tutoring notes, because there might be things in the tutoring notes that now jump out at you that you didn't notice before you'd actually started struggling with the problems. Oftentimes the tutoring notes are not the most fascinating reading if you're just reading them on your own, but if you've just been struggling to do a bunch of problems, then you might see parts of the tutoring notes that can be helpful to you. So I guess the point is keep going back and forth between the new problems and the worked problems. That way you'll be able to execute the strategies more carefully. Remember, what is the purpose? Or something else was, I think one thing you kind of forgot when you were doing these is I think you forgot to alternate sometimes between acid-base and nucleophile electrophile, right? But that was one of the main themes from the tutoring session. So again, if you had reviewed the tutoring notes, that might have been something that would have jumped out at you. So in any case, remember, most of the homework exercises are going to be almost identical to things that we did in the tutoring. Because the point of them is to let you practice the techniques we just went over. So when you're doing the homework exercises, what you should be asking yourself is, what techniques from the tutoring am I supposed to use on this? Now, every once in a while, I'll give you a problem that's a little bit different to stretch you a little bit and make you think a little bit. But I don't put in too many of those, and I don't make you stretch too far. Most of the problems are going to be pretty similar to what you've already done. So the purpose is to try to use what you've already gone over. All right, and I'm just mentioning that because the better we're able to do with that, the faster we'll be able to go. So you can see all this stuff that we're going over here I think is extremely valuable. So why don't instructors cover this in class? I think this material we've gone over is very, very valuable. I think it's already improved your OChem skills a lot. So why don't instructors cover it? It's because it takes too long. You know, the instructor doesn't have time to go over all this material. So this can be kind of time consuming, and we want to be able to cover as much material as we can. So the way to get the most out of the tutoring sessions is to restudy each tutoring session carefully and try to absorb what the techniques are. That way in the next session we don't have to spend too much time reviewing, but we can go on to the new stuff. So let's take a look then at the next problem here. Let's see, so I'm not sure if we're going to do all of these now together, but some of them I think we'll need to do. Let's see. Okay, so let's move on down to the hydronium problem. Let's try that problem.
Okay. Okay.
So, does it look like we're done, or does it look like we need another step?
Not quite done.
Good. And what type of reaction do you think we need next?
Acid base.
Good. So actually, that's actually an interesting next step. Yeah, that's certainly. So that next step you wrote there is totally plausible, totally reasonable. Do you see that if you did that, you would kind of get a chain reaction? You'd make another. You kind of make another cation, and the reaction could kind of continue. Okay, so that actually is quite plausible. That's not the way it's usually going to be drawn in the answer key, though. So what the problem here is you were having trouble finding the base. Well, maybe zoom out a little bit here. Who do you think is probably the solvent? What do you think is probably the solvent for this reaction? The solvent wasn't shown, but who's probably the solvent? The solvent here is probably water.
Okay.
Maybe that's really not obvious, but the solvent here is water, so that would be a better candidate.
Sure, I see that. Because that would then give us a better product.
Okay, fair enough. Let's zoom out so we can see this whole reaction on the screen at one time. Okay, what's the name of H3O+?
Hydronium.
That's right, hydronium. That turns out to be a really important reagent in organic chemistry, so this is a good opportunity for us to discuss that in more detail. So, first of all, one thing to keep in mind is that the solvent is not always shown when people write out organic chemistry reactions. Sometimes they show the solvent, sometimes they don't. If they don't show the solvent, maybe you don't know what the solvent is, but sometimes there's kind of a solvent that's implied. So here, when you use hydronium, what should you assume is the solvent?
Water, I guess.
Because, do you see, hydronium is just protonated water.
Okay, yeah.
Now, I'd like you to compare this example with the two examples previous, with the sulfuric acid and water. So compare this example with the hydronium, point to the example with the sulfuric acid and water, so I know we're looking at the same thing.
The one with the star, right?
Yeah. So, sorry, it was hard for me to find your cursor. Good.
Yeah, it's a little hard, sorry.
So can you compare those two? All right, good. So if you can compare those two, do you see how they're pretty much the two identical reactions?
Yeah, I see that.
In fact, they really are the identical reaction, because what was the solvent in the upper reaction?
Water as well.
And what was the solvent in the lower reaction?
Water.
Even though we didn't write it, that's assumed. And what role did the H2SO4 play?
Strong acid.
That's right. And what role does H3O+ play?
The same role.
Strong acid. So basically, they're both a strong acid plus water. They're both a strong acid plus water. They're basically the same exact conditions written in different ways. Notice in the first reaction, you had the sulfuric acid protonate the alkene, right? What if the sulfuric acid had protonated the water instead? What would you get if sulfuric acid protonates water?
H3O, hydronium.
So notice they really are the same identical situation. They're the same identical situation, just written in different ways. So what does H3O+ really mean? H3O+ really means a strong acid in water. Okay. H3O+ is just kind of a shorthand or a code. H3O+ is kind of a code for a strong acid in water, probably sulfuric acid in water. So in that bottom example with the H3O+, that probably is sulfuric acid in water. We just haven't shown the sulfuric acid, we've just shown the protonated water because you get the same results either way. Okay, so this is something we haven't really talked about before, but hydronium is a very common reagent in both semesters of organic chemistry. It's very likely to come up on your DAT as well. So this is a good opportunity for us to get a clearer idea of what hydronium really means. What does hydronium really mean? It means a strong acid in water solvent.
Okay.
So it behaves just like that. Or all you really need to keep in mind for our purposes here then is what's the solvent when you see H3O plus?
Water.
Water. It's just because it's just showing, and it just means that there's a strong acid like sulfuric acid in water. So the solvent is water, and there also will be some protonated waters floating around H3O plus. So basically, my point is that these two examples we're examining are the same exact example. They're just two different ways of writing the same thing. Sometimes there's two ways of writing the same thing. Okay. All right. The key for the mechanism here was, again, one more time, what's the solvent when you see hydronium?
Water. That
was the key to finishing that step. Okay. So we learned some important things there. So obviously you should be taking notes on this. So now that we've shifted from kind of reviewing the homework, and now we're kind of just going over some more new material here. So this should be in your notes, just like any other material we talk about. We learned some important things here about hydronium. Okay, I think the next example you probably know how to do, so we'll leave that as homework. Let's see. Okay, so let's go on. Then we'll skip the alkyne and go down to the next example.
Okay.
Let's try this next example. Try to come up with reasonable arrows here.
Okay.
Okay, that was excellent. That was a very good process. What is the name of H3O plus?
Hydronium.
Hydronium. We were just talking about that. What's the solvent here?
Water.
How do you know? I didn't say it was water. Well, we just kind of memorized that. Hydronium usually uses a water solvent. Good. Notice you needed that to complete the mechanism. So that was a good application of what we were just talking about. By the way, what role did the carbonyl oxygen play in the first step?
Electrophile. Oh, in the first step, oxygen. Sorry, I was looking at the second step. Played the role of base.
Yeah. Is it a strong base or a weak base?
A weak base.
But the hydronium is a strong acid, so the reaction was still reasonable. So to review, what role did the carbonyl oxygen play in the first step?
Weak base.
Excellent. Good. Let's scroll back up and take another look at question 10. What was the answer to question 10?
Weak base.
Right. Or it could also it's often also that kind of pseudo-leaving group, like you said. Remember when you did that question originally, though, you had left out the weak base answer. So I just wanted to illustrate. We just saw an example. There's many examples where it's very important that you often start with the carbonyl oxygen acting like a weak base. Okay, very good. So let's scroll back down to where we were. So what was the purpose of the hydronium? How did the hydronium help this reaction?
It made the oxygen more positive. It made the molecule electrophilic.
That's a very good answer. That's right. By making the oxygen positive, it made the carbon electrophilic. The carbon was already electrophilic, but now it's a much better electrophile. Okay. Good. Okay, good. So now let's try the next example.
Okay. Sorry, that's kind of crossing problems.
Looks like I should space these out more when I send them to you.
Sorry about that.
That's a good idea. That's a good idea. It's good that you put in that arrow. That's important.
Thanks.
All right, and that's good that you're numbering those. That's important.
Okay. So we need some more water. Okay.
Check your work on that problem.
Didn't write the charge.
Yeah, without that charge, the reaction doesn't make any sense. Without that charge, what's the most important thing to get right in that? The charges. That might seem like a minor detail, but that's very important. Okay, so we always have to be super careful. The charges are even more important than getting the bonds right. After all, erase that charge for a moment.
Okay.
So what role is the water playing in that step?
Base.
Is it a strong base or a weak base?
A weak base.
Yeah. And what role is the other OH playing?
Acid.
Acid. Now, is a neutral oxygen a strong acid or a weak acid?
A weak acid.
So is it reasonable to have a reaction between a weak acid and a weak base?
No, it's not.
No. So without the positive charge, that step doesn't make any sense. All right,
Okay.
so let's go back and put that positive charge in. Okay, so that's pretty important. All right, so anyway, let's zoom out so we can see the whole reaction here. So the main thing I wanted you to do was to compare this example with the previous example.
Yeah, they were the same problem.
Yeah, they're just the same problem written in two different coded ways. This is what we were already talking about a couple minutes ago. What does H3O plus mean? It really just means a strong acid in water. You can really imagine it as sulfuric acid in water. So it shouldn't surprise us that when we actually draw out the sulfuric acid in water, we get the same exact thing. Okay, so that's an important thing to learn about hydronium here. Okay, let's see. I think we'll leave the next example as homework. So let's move on down to the NaBH4 example.
Okay. Okay.
Okay, that's good work, and it's good that you knew when to stop. So I think you identified that the left-hand molecule is kind of what we would call the main molecule here. It's a little bit hard to tell, but that's the main molecule, so we are done because that main molecule now is neutral. Okay, let's see here then. So what role did so the NaBH4, that is called sodium borohydride. That's a pretty important reaction, so you might want to write down that name, sodium borohydride. Do you see why that's a logical name?
Sure, yeah.
So what does the sodium refer to?
The Na?
Yeah, the sodium. Good. And what does the boro refer to?
The boron.
And what does the hydride refer to?
The hydrogens.
Now, do you remember what exactly is hydride? What is the formula for hydride?
It's a negative charge hydrogen.
So do you see why this is called hydride? The hydrogens don't actually have negative formal charges, but they act as if they did. Technically, the negative formal charge is on the boron, but we've seen that it's actually the hydrogen that's going to act like the nucleophile. So
I see.
even though it doesn't have H minuses in it, they act like they were H minuses. It acts like it's a source of H minus. So the name is extremely logical. So what role does sodium borohydride play in reactions?
It plays the role of a nucleophile.
Exactly. That's right. That's what it's doing. It's a nucleophile. Then how about the alcohol? What role was the alcohol playing here?
The alcohol was acid.
Good.
An acid.
Strong or weak?
A weak acid.
Weak acid, but it can protonate the negative oxygen. Also, what do you think is the solvent here?
The alcohol.
That's right. So the alcohol is the solvent. And then oftentimes the solvent is used for the protonation step. Oftentimes the solvent is used for that second protonation step. Okay. All right, so that's one of the things I wanted to focus on with you today. That's one important reagent. Let's try the next example.
Okay. Okay.
Okay, that's it. Yes. Notice this is kind of a boring, uninteresting reaction. You're not going to get the Nobel Prize for carrying out this reaction in your lab. There aren't even any carbons involved here, right? So it doesn't seem like something an organic chemist would do on purpose. This is kind of, so the point is, so what role did the lithium aluminum hydride play here?
It was a base, strong base.
Right. What other role can lithium aluminum hydride play besides base?
Nucleophile.
But it didn't get to do that because instead it acted like a base here.
Yeah.
So the point is, this is something you'd probably want to avoid if you were a chemist, because you want the lithium aluminum hydride to be a nucleophile, but instead you just destroyed it. Now you're going to have to go order some more lithium aluminum hydride because you just destroyed the ones that you had by doing this acid-base reaction. Okay, let's go ahead and try the next example. Do you know what those numbers mean in the next example? I don't think we've talked about that. What does it mean when the reagents are numbered?
Is that steps? So the first step would have the lithium aluminum hydride, and then on the second step you would add the hydronium?
Good. Now we have to be a little bit careful here, but the key thing is you said is add. There's two different meanings to the word step. It's a little ambiguous. After all, mechanisms have steps, right? Mechanisms have steps, but the chemist doesn't have to add anything for the second step of a mechanism. It just happens automatically. For example, take a look at the sodium borohydride reaction up above. How many steps were there in that sodium borohydride reaction?
2 steps.
Yeah. Notice the alcohol didn't participate until the second step, right?
Right.
Does that mean the chemist waited until the second step before they added the alcohol?
No.
It was there all along. It just didn't participate till the second step. So the key thing is there's a difference between writing reagents with a comma and writing them with numbers.
I
If
see.
the reagents are written with a comma, does that mean the chemist added them simultaneously or one after the other?
Simultaneously.
Right. And if the reagents are written with numbers, does that mean that they were added simultaneously or one after the other?
One after the
Right.
other.
I think you actually already knew that. That's basically what you said before, but I just wanted to make sure that was clear. So what you said was right. So the numbers here mean that we're going to wait until the first step has finished before adding the H3O plus. The numbers mean wait until the first set of reactions is finished before adding the H3O plus. A comma means everything's added at the same time. What was the solvent when you used the sodium borohydride?
The alcohol.
Right. I didn't show what the solvent was with the lithium aluminum hydride, but maybe do you know how to write an ether? Do you know how to write an ether? Can you write down an ether? Do you know what that is?
Is it, trying to remember, seems, is there carbonyl in an ether?
Okay, no. Well, we haven't talked about that. It's an oxygen connected to 2 carbon chains.
Okay.
So let's use an ether as the solvent. Yeah, like that. That would be dimethyl ether.
Okay.
Okay, so let's try using an ether as the solvent in step 1 of the lithium aluminum hydride reaction. Let's try using an ether as the solvent in step 1 of the lithium aluminum hydride reaction. How would you write that?
Okay.
So comma, and then an ether. So you wrote the dimethyl ether. Okay, good. Notice you put in a comma to show they're both being added in the same step. Good. Go back and erase. You can go back and erase the ether that you wrote up above, because that was just writing. Okay. See if you can figure out what's going to happen now in this reaction.
Okay.
Good. Okay, that's very good. That is right. That's good. That's okay. Let's continue, but that's good.
Okay.
Okay, that's good. You figured that out. Good. So let's look at the whole thing together here. Okay, very good. So what role did the lithium aluminum hydride play in the first step?
Nucleophile.
Good. That left the oxygen with a negative charge. Nature's not happy about that, but there's not really much that nature can do about that until we add the hydronium. The negative charge is stuck there until we add the hydronium in the second step. In fact, that's why the chemist added the hydronium. The chemist added the hydronium so we could get the neutral alcohol in the next step. So compare this with the sodium borohydride reaction up above. Do you see that we actually ended up getting the same thing in both reactions? in the sodium borohydride and the lithium aluminum hydride reactions?
Yeah.
Notice that in both, would you agree that the electrophile was the same molecule in both cases, the same carbonyl?
Yes.
Yeah. What role did the sodium borohydride play?
Nucleophile.
And what role did the lithium aluminum hydride play?
Also nucleophile.
Right. And do you see that we got the same alcohol product in both cases?
Yeah.
All right. So sodium borohydride and lithium aluminum hydride are fairly similar to each other. But why did we have to do this in 2 steps, whereas we did the sodium borohydride in 1 step? So notice that in this step, we didn't add so what was the solvent in step 2?
The hydronium?
Yeah. Well, that's not the solvent.
Oh, water.
Right.
Yeah.
Why couldn't we just use water as the solvent in step 1? Then that could have done the protonation. What would have gone wrong if we had used water as the solvent in step 1? Notice we used an ether as the solvent in step 1. So,
right.
But the problem with ether is that it couldn't protonate the oxygen. Why couldn't we just use water in step 1 and use that to protonate the oxygen? What would go wrong if we used water as the solvent in step 1?
We would just form hydronium from the hydride, from sodium aluminum hydride.
Okay, you're on the right track, except it doesn't form hydronium. In fact, look at the middle reaction. We already figured out what happens when lithium aluminum hydride is in the presence of water. We already did that in our middle reaction.
Oh, I guess, okay. Yeah. Okay, sorry, what was that question?
What happens when lithium aluminum hydride is in the presence of water?
It forms hydroxide, and I guess that is dihydride.
Hydrogen gas.
Hydrogen gas, yeah.
That's right, not hydronium. But anyway, the important thing is, what type of reaction happens when lithium aluminum hydride is in the presence of water? Nucleophile electrophile or acid-base?
Acid-base.
Which is probably not what we want. Remember how we said that was a really boring, uninteresting reaction in the middle that just destroys your lithium aluminum hydride. So what we're trying to do here is to learn that we have to be careful about what solvent we use with lithium aluminum hydride. Maybe I'll go back to my screen.
Okay.
So, do you remember this complicated table that we went over here? Lithium aluminum hydride will act like a base if there's any acid around. Otherwise, even a weak acid.
Yeah.
Otherwise, it will act like a nucleophile. Now, what's the purpose of these reagents? What do we want them to act as? Bases or nucleophiles?
Would it depend on...
Yeah, I haven't really quite specified that, but almost always we want these to act as nucleophiles.
Okay.
I haven't really made that clear, but these are things we want to act as nucleophiles. So we have to keep them away from weak acids because the weak acids will destroy them. Basically, maybe I'm kind of overcomplicating these. All right, tell me when you have this in your notes.
Okay.
Okay. So these are reagents that chemists use because they want them to act as nucleophiles. But they have a drawback, which is that they're also very strong bases. So they have to be kept away from acids to avoid acid-base reactions. Well, to put it more simply, that what usually comes up in OChem is you have to keep them away from OH groups, because OH groups are acidic. They're only weakly acidic, but that's still too acidic for these reagents. Okay.
So it looks like they would act as a base before they would act as a nucleophile, if there were any kind of acid there.
Why didn't I put it that way? Yes, that's a good way of putting it. Yes, exactly. So there's two different roles that these reagents can play. What are the two different roles they can play?
They can act as nucleophile or base.
Right, and they're strong bases. If they have a choice, if they could go either way, which one will they choose?
Base.
That's right. So, but what do we want them to do?
Nucleophile.
So we have to keep them away from acidic OH groups, because otherwise they'll go down the wrong path. All right, actually I did kind of put it that way up here. That's what I meant by this. These reagents act like bases in the presence of acid. Otherwise they'll act like nucleophiles. So what you said is exactly right.
Okay.
Okay.
Yeah.
Okay. Do you see how that's different from these two reagents? These are reagents that chemists use, at least in introductory OChem. These are reagents that are used because we want them to act as bases. So almost all the reactions in OChem that use these, they will be acting as bases. But these are reagents where you want them to be nucleophiles, so you have to keep them away from acids so they won't act like bases. Okay, and the thing to especially worry about is OH groups. So maybe let's go back to your screen. Okay, so what solvent did we use? So when the lithium aluminum hydride was reacting with the carbonyl, what solvent did we use?
An ether.
Right.
Dimethyl ether.
Why couldn't we just use water?
It would have caused an acid-base reaction with the lithium aluminum hydride.
Which is not what we wanted. Good.
Right.
So do you see, that's why we had to wait until the lithium aluminum hydride had already done its work before we added the water in the second step.
Yeah.
That's the point. So we had to wait until the lithium, that's why these have to be numbered. You have to wait until the lithium aluminum hydride's job is done before you add the water. We don't need to worry about destroying the lithium aluminum hydride when we add the water in the second step, because the lithium aluminum hydride has already been destroyed by acting like a nucleophile. Okay. Now, you can see what would go wrong. What would happen if we did add water? Well, then you would have gotten the middle reaction, where we make the hydrogen gas. But that's a very boring reaction that you want to avoid. Okay.
Yeah.
Now,
it looks like it would not have reacted with the carbonyl if we had used water as a solvent. Or
can you
if
say
it
that
did,
one more time? I didn't hear you.
Oh, it looks as though had we used water as a solvent,
yes,
that that carbonyl reagent would not have reacted really with
that's
anything.
Right, exactly. But that's probably what we wanted. We wanted to turn this carbonyl into an alcohol. But if we screwed up and used the wrong solvent, the carbonyl would just sit there. That's right. Okay.
Okay.
Now compare this with the sodium borohydride reaction. What role can sodium borohydride play?
Nucleophile.
Is it a strong base?
No.
Do you remember we talked about that in our previous session? Sodium borohydride is not a strong base. It's a weak base. That doesn't turn out to be too important, but it's not a strong base. So, notice that what was the solvent we used with sodium borohydride?
An alcohol?
Did we need to worry about the sodium borohydride doing an acid-base reaction with the alcohol?
No, they're both weak.
They're both weak. In fact, we could have used water. Could we use water with sodium borohydride?
Sure.
Yeah, because they're both weak again. It's more conventional to use alcohol, but you could have used water as the solvent there.
Okay.
So the point is, does lithium aluminum hydride have to be kept away from OH bonds?
Yes, they do.
Does sodium borohydride have to be kept away from OH bonds?
Nope.
Why? Because lithium aluminum hydride is a strong base, and sodium
Yeah.
borohydride is only a weak base. Okay, we're not going to explain why that is. We just memorized those facts about them. Okay, so these are common patterns. So we get the same exact reactions with sodium borohydride and lithium aluminum hydride, but with sodium borohydride, we can do it all in one step because we can add, these are what are called protic solvents. When there's a hydrogen and an oxygen, that's a protic solvent. So we can add a solvent that can do the protonation along with the sodium borohydride. But with the lithium aluminum hydride, we have to do them as two separate steps. Okay, I hope that's making sense. Well,
Yeah.
Anyway, let's take a look at the next example. Try the next example.
Okay.
Okay, good. Notice that the product here was very boring. You're not going to get any prizes for making ethane. That's probably not what the chemist wanted to have happen here. But that is what would happen. So what role did the Grignard play in this reaction?
Base.
Base. But what do we probably want Grignards to do?
Be nucleophiles.
So it looks like the chemist screwed up because they should have kept the Grignard away from water. Okay. So now they have to just order more Grignard reagent because they carelessly destroyed the Grignard they have. Let's try writing down the mechanism then for the next step, the next reaction.
Okay.
Okay, very good. So what role did the Grignard play in this reaction?
Nucleophile.
Which is kind of what it's intended to do. Now, what was the solvent in the second step?
The water.
Right. Why couldn't we just use water as the solvent in the first step?
Because it would have messed up the Grignard, making an acid-base reaction where we wanted it to be nucleophile electrophile reaction.
That's right, exactly. It's the same exact thing as with lithium aluminum hydride. That's right. So, so what was the solvent in the first step? Well, we didn't say what the solvent was, but what's a solvent that's commonly used with Grignards? Again, ethers. Ethers are commonly used, but because the solvent wouldn't do anything, it's oftentimes not even written. But you could assume that the solvent in the first step is likely to be an ether, but who cares because it's not going to do anything in the reaction. Why is an ether a better solvent for a Grignard than water?
Because it does not have any OH groups. It's not acidic
That's
at
the
all.
key. Very well put. Very well put. Ethers are not acidic. They're not even weak acids. So that's exactly right. Ether is a good solvent here because it's not even weakly acidic. Okay, by the way, what would have happened if instead of adding H3O plus in the second step, what would have happened if we just added water in the second step? If we just added water instead of H3O plus, what would happen?
It looks like it would still carry out, but it would be a weaker reaction. You'd end up with a hydroxide.
Would you still get that acid-base reaction in the second step?
I believe so.
Because the O minus is a strong base.
Yeah.
So my point is H3O plus is overkill.
Okay.
Because what type of what role is the O minus going to play?
A strong base.
Right. And what role does H3O plus play?
Strong acid.
Do you see how that's overkill? Do you need a strong acid to react with a strong base?
No.
No, you could just use a weak acid. Okay. Now, the whole purpose here is that the chemist wants to protonate the oxygen, so that there's nothing wrong with overkill. That way they make sure that they get 100% yield of protonation. I just wanted to point out that some organic chemistry classes write the second step as H3O plus. Sometimes they just write it as water. It kind of gives you the same result either way. H3O plus seems a little bit better because then you're even more sure that all of the O minuses will get protonated. But even if you only added water, then you would get almost 100% protonation anyway. So H3O plus is the most common way of writing it, even though it's kind of overkill. Even if you only added water in the second step, you would probably get basically the same thing. I guess I'm just trying to say some textbooks write the second step as H3O plus. Some of them write it as just H2O. So again, on the DAT, you might see it. I don't know which way they tend to write it on the DAT or in your instructor's class. I think the most common thing is to write it the way I'm writing it, with H3O plus. But the fact is, even water would probably give you pretty much the same outcome, because you don't need a strong acid to react with a strong base. Even a weak acid would do the trick. The important thing is we can't add any water at all until the second step. If we added the water in the first step, it would destroy the Grignard. Okay, so the important thing is that the pattern for the Grignard is the same as for lithium aluminum hydride. Okay?
Okay, yeah.
These are pretty important reagents. They oftentimes, these reagents oftentimes come up in the first semester. I don't know if you saw them in your first semester, but they're definitely really important in the second semester. And I'm sure that would be important on the DAT too. Let's see, so now we understand those a little bit better. Let's see. Let's see. All right, let's scroll down. I'm not going to go through all of these. I'd like you to do these again, try these instead as homework to save time for the tutoring session. So let's do the second alkyne reaction here. Let's do the second alkyne reaction.
Okay.
Okay. Good. So what role did the alkyne play in the first step?
Base.
Right. What makes that reasonable?
The carbon-carbon pi bond?
Yeah. Now, we've mainly focused on how alkenes are weak bases. But following the same rule, alkynes should also be weak bases because they also have carbon-carbon pi bonds. Good. Why did you put the positive charge on carbon 2 instead of on carbon 3?
To make it acceptable as a secondary carbocation.
Right. This is kind of an unusual carbocation because we haven't seen, I don't think you've ever seen a carbocation on a double bonded carbon before. But you just guessed that it would follow the same rules as before, and that was a good guess. This follows the same rules. Even with the double bond, it's better to be on the secondary than the primary position. So that was correct. All right. And then remember that on the earlier homework problems, you were having trouble because, well, what did you use the chloride for in the next step?
As a nucleophile.
Yeah, remember on some of the earlier homework questions, we were getting those incorrect because we were forgetting that the halogens could be nucleophiles. But here we got that correct. Here the halogen was the nucleophile. Notice this is kind of an unusual reaction. You and I don't think we ever studied this before. This is something you just figured out, an alkyne reaction. I don't think we've had any products before with a halogen on a double bond. But the point is, by learning these general rules, we can predict what can happen in reactions we've never seen before. So these are powerful techniques. Obviously, it'll be all the easier after you've studied it. It makes it easier to remember the reactions. But even if you haven't studied it, we can already have a very strong guess as to what would happen here. Okay, good. So that was a good execution on that. It's good that you didn't get... you just applied the previous rules, even though it was with an alkyne. So let's go ahead and try the next example.
Okay.
Oh, did you notice the hint?
Well, that falls off. Yeah. Sorry. So that would just fall off. Thank you.
Okay. Why did you have it fall off of 6 instead of falling off of 3?
I don't know.
So.
Oh, I guess it would be a tertiary, do you call it? Tertiary carbocation? And that's better than an unacceptable primary carbocation.
Okay, good. Now, careful. What is the meaning of a tertiary? What's a tertiary carbon?
Oh, you know what? It's a secondary because the other atom there is an oxygen.
Right. So what's the definition of a secondary carbon?
It is a carbon that has 2 other carbon bonds.
Yeah. So secondary doesn't mean attached to 2 things. It means attached to 2 carbon chains. And tertiary doesn't mean attached to 3 things. It means attached to 3 carbon chains.
I see.
Okay.
Yeah.
Okay. Now, this carbocation actually is a little bit unusual because there's also some resonance effects here. But in any case, it is secondary, so that by itself would stabilize it. What type of carbocation would we get if the oxygen fell off of 3?
Primary.
So that definitely is not a good idea. So you might have kind of lucked out here. Maybe you didn't think about it. But in this case, we do want it to fall off of 6 and not 3, because otherwise we would get an unacceptable carbocation. Okay? So are we done?
Not yet.
Okay.
Okay.
Okay. Check your work on this example. Check the products that you've drawn.
Yeah, I'm doing something wrong.
Okay, so we got a little bit lazy on that one. You had to redraw one of the hydrogens to show it being taken, and we got a little bit lazy and we didn't erase the 2 when we did that, and that ended up messing us up. Okay, so that's just a little pesky task that we have to take care of on a lot of these problems when we redraw. Okay, let's see. So what type of reaction was the first step? Nucleophile, electrophile, or acid-base?
It looks like an acid base.
Right. That's a no-brainer, because when we know that when you start with a strong acid, you always start with an acid-base reaction. So that was good. All right. Then the next step was the leaving group just falling off, as given by the hint.
Yeah.
Then what type of reaction was the third step?
It was nucleophile to electrophile.
Right. So notice there's actually 2 different types of nucleophile electrophile reactions. Sometimes the nucleophile attacks the electrophile and kicks off the leaving group at the same time.
Yeah.
But sometimes the leaving group leaves first, and then the nucleophile attacks the electrophile, if you see what I'm saying. So those are just 2 patterns.
Yeah.
That's just a little complication. Sometimes the nucleophile attacks the electrophile and kicks off the leaving group simultaneously, and sometimes the leaving group just leaves on its own, and then the nucleophile. So what usually happens after the leaving group leaves on its own?
Nucleophile attacks the electrophile where the leaving group
Because
left.
that's going to leave a positive charge behind. Okay,
Yeah.
good. How do you know which one it is? How do you know if the leaving group will leave simultaneously or in the previous step? Well, you just kind of have to learn the details for each individual reaction. We're not going to try to learn that right now. That's why I'm just giving you the hints here. When you study the individual reactions, you learn how to figure it out. Obviously, the leaving group can't fall off on its own unless it's going to leave a stabilized carbocation behind. So that's one thing you can look for. But that's not really good enough to tell. Sometimes even if it would leave a reasonable carbocation, it's still not going to leave. So basically, we haven't learned how to figure out which one it is, so I'm just giving you hints. So you should just, generally, you should just assume that the leaving group will leave at the same time as the nucleophile attacks, unless you've learned specifically otherwise. Okay. And then after the nucleophile-electrophile reaction, what type of reaction did you do next?
Acid-base.
Right. Who did you use as the base? The alcohol. Now, what's the solvent for this reaction?
Water.
So who else could you have used in the base, and that's as the base in that step?
Water.
Okay. There's nothing wrong with what you did. What you did is fine. In class, you'd probably see water used for that instead. I don't know. All right. So I guess,
Okay.
actually, I don't know. It doesn't make much difference. But you should keep in mind you could have used water for that step as well. But there's nothing wrong with the way you did it. Okay. All right. All right. So so we went over some important stuff there. Some of the stuff there was stuff from the previous session that I think you might have forgotten a little bit. So we reviewed some stuff from the previous session you might have forgotten. But we also went over some new material that we hadn't talked about before. Hopefully now we're understanding this table here a little bit better. Remember that strong acids are pretty simple. If you see a strong acid, you know you're going to start with an acid-base reaction. But strong bases are trickier. Some strong bases always start with a strong base reaction. Other bases, you want them to act as nucleophiles, so you have to keep them away from acids so that they'll do that. And then O-, I haven't really been working with you on because that can just go either way. O- can be either a nucleophile or a base. You just have to memorize what's going to happen for each type of reaction separately. So O- can be kind of tricky. All right?
Okay.
So what role does O- play in reactions?
O- can be either a base or a nucleophile.
Yeah. What is it, a strong or a weak base?
Strong base.
So how do you know which one it's going to do? Well, it's tough. You just have to learn you have to learn what it's going to do for each particular type of reaction as you study in OChem. It's hard to predict ahead of time. Okay. So I haven't given you many examples of that. Let's see, because it's something you just learn with the specific reactions. What we're trying to go over now are things that apply to almost the whole course. There's a bunch of ideas that apply to almost the whole course that you don't have to memorize them separately for each reaction, but there are still some things that have to be memorized for each reaction, and that's what happens with O-. All right?
Okay.
Okay, so let's do more of the same type of problem. Try to come up with some reasonable arrows for this reaction. You can try this on your screen.
Okay. Okay.
All right, all done?
Sorry, I didn't mean to. Forgot to write that.
Okay, all done?
Yeah.
Okay.
Looks like they may have wasted some Grignard.
Okay, excellent. I'm glad that you said that. So that's the point here. So what role did the Grignard play here?
It played the role of base.
All right. Do you think that's what the chemist wanted?
Hopefully not.
Now, what did they probably want it to do?
Be a nucleophile.
That's right. So this chemist has set this reaction up incorrectly. So how would you fix this? Try writing down a similar reaction that would accomplish what they probably wanted to have happen here.
Okay, I think that's all.
Okay, we can't. So we usually don't stop when there's a charge, but there's no way to get rid of this charge. But
Yeah.
that's probably not what the chemist wanted either. Usually we're trying to make neutral compounds in the chem lab. There you
maybe
go.
Like that.
That's right.
Which I guess you could just use H2O.
That's right. Sometimes some textbooks just use water, but I think it's more common to use H3O plus. So we'll try to do that.
Okay.
The whole point here is that we want to make sure the protonation happens, so we may as well go for the overkill and use a strong acid, not just a weak acid.
Okay, that would be the product.
Okay, check your work on this last step. There's a mistake somewhere in that, what you wrote down for the starting materials or product for that last step.
Yeah, I should have had a...
What's the most important factor in organic chemistry?
The charges.
So we have to be very paranoid about getting those exactly right every time. Okay.
Okay.
Okay, so yeah, so I wanted to study that when you use Grignards, those are two-step reactions. You have to add the reagents in 2 steps. Remember that I think we've actually made some really good progress now on when I give you the starting materials, I think in many cases you can predict what's going to happen. So now we need to move to the next level of difficulty. We have to get to the point where you can come up with the reagents yourself. Because many problems in OChem, you have to come up with the reagents for a synthesis problem. So if you're trying to do a synthesis with a Grignard, you usually have to add the reagents in 2 steps. That's what we're trying to learn here. When you're adding the reagents for a Grignard, you have to add them in 2 steps. Now, the way you wrote this is correct. It's not really kind of the usual way of writing it, though. So I'm going to go back to my screen to show how this would usually be written. This is the same exact thing as you wrote. It's just the more usual way of writing it. It's weird to just put. People don't usually just put a solvent next to the step. They put the main reagent next to the step as well. So this is how this is usually written.
I see.
In fact, because this solvent is so boring and it's not doing anything, oftentimes the solvent is just left out, and they just write it like this.
Okay. Yeah.
So it can go either way. Sometimes they write the solvent. Sometimes they just leave it out. But this is more common. But you would get full credit for the way you wrote it as well. It made sense. It's just not the conventional way of writing it. Okay, good. Okay, so let's draw the arrows for this step.
So if we wanted to make that be more interesting, we would not add water and use an ether as a solvent instead.
Okay, excellent, good. So that's good that you made those comments. That was my point here. Excellent. So it looks like the chemist messed up. The chemist thought that they had everything perfectly planned, but they got lazy and they didn't think carefully about what solvent to use. You can see how this could happen because what's the most common solvent that's used in chemistry?
Water?
Yeah, it's natural to use water as your solvent, so you can see how people can fall into this trap. So I don't know the exact history here, but I can imagine that when people were first studying these types of reagents, there was probably a lot of frustration when they weren't getting the reactions that they wanted. And eventually somebody must have figured out, oh, wait a second, maybe our solvent is messing up the reagents. It probably wasn't obvious. So it's easy to forget, but every single one of these ideas that we talk about had to be painfully and laboriously learned in the lab by trial and error. But now we can benefit from their painful experience, and we know from painful experience that water is not a good solvent to use with these reagents. Okay, so try to write down a better set of, let's try to write down a reaction that's more likely to accomplish what they were probably trying to do here.
Okay. Oh wait, what's that? Hydrogen.
Good. That actually is a really common mistake that people make. People oftentimes transform that hydrogen into a carbon accidentally. So that's good that you caught that. Notice that forcing yourself to number helped you to see that mistake. So that's good that you caught that. You haven't really studied this yet, but this is what's called an aldehyde. But if you change that into a carbon, it would be a ketone. It would be a whole different molecule. Okay, so anyway, we can continue.
Okay. Okay.
Okay, excellent. Very good. So point to the nucleophile. Do you remember what do we call that type of molecule?
Yeah, alkyl lithium.
Alkyl lithium. That's good that you remembered that. Yeah, that's called an alkyl lithium. Alkyl lithiums are almost identical to what other type of molecule?
Grignard.
Yeah, there's almost no differences for the introductory course between an alkyl lithium and a Grignard. So you can see we ended up with pretty much the same reaction here, either way. Okay, excellent, good. Good, so I'll go back to my screen. All right, let's try the same thing in this reaction. Actually, I have a different idea.
Okay.
Do you know what this stands for?
Methyl hydroxide, I guess?
Yeah.
Methyl alcohol.
Yeah, methyl alcohol. And what does this stand for?
Ethyl alcohol.
Okay, we haven't used those abbreviations before, but it's good to know what those stand for. Okay, so let's try this reaction. So, oftentimes, reagents are written in condensed notation like this, and then the student has to write them in bond line notation. Okay.
Okay.
Let's try this on your screen then.
Okay.
Okay, so does this look like a successful reaction?
No.
What went wrong?
I can't remember the term for it. The lithium aluminum hydride
That
was.
is the term. Yeah,
Oh,
that's the term. That's a pretty logical name, right? Yeah,
yeah.
good. So that is the correct name, lithium aluminum hydride. Good.
It was in the presence of. I can't remember what it was called when it has an OH. I mean alcohol, but
You could call it a protic solvent.
that's what it
Or
was.
basically the point is, what role is the protic solvent going to play here?
Acid.
Yeah, it's in the presence of a weak acid, so...
Okay. Yeah. In the presence of a weak acid, so that made the lithium aluminum hydride act as a base rather than probably what was wanted as a nucleophile.
Because notice that the carbonyl is just sitting there, not doing anything.
Right.
That's the interesting molecule that they probably wanted it to react with. All right, well, let's try to come up with our own synthesis that will be more successful.
Okay. Okay. Ah. Okay.
All right, yes. So we're starting to make that mistake sometimes. So it's important to make sure that we're getting all the charges correct. Those seem like boring details, but those are very important. Okay, so good. So now we fixed this reaction. What was the name of the nucleophile here?
The lithium aluminum hydride.
Right. So we had to keep it away from the protic solvents in order to make it act like a nucleophile. So what might we be using as the solvent in step 1? Could we use water as the solvent in step 1?
No, we could use...
Could we use alcohol as the solvent in step 1?
No.
No. So you were saying?
Something not acidic, like an ether.
Yeah, ethers are good. Sometimes people draw the ether, sometimes they don't. So it's okay that you didn't draw it. Sometimes you'll see it drawn, sometimes it's not. Sometimes it's left out because it's not really participating in the reaction. Okay, good. I'll go back to my screen. Let's try this example.
Okay.
Okay, let's scroll up a bit so we can also see the previous. Okay, so what was the solvent with the sodium borohydride?
It was methyl alcohol.
Yeah, it's called methanol. So,
Methanol.
or methyl alcohol, methanol. So are alcohols acceptable solvents for sodium borohydride?
Yeah.
Are alcohols acceptable solvents for lithium aluminum hydride?
No.
Why not? What's the difference?
Because lithium aluminum hydride is a strong base, whereas sodium borohydride is a weak base.
That's right.
And it would react.
That's well put. It's exactly right, because lithium aluminum hydride is a strong base and sodium borohydride is a weak base. Notice we kind of have to just memorize that. That's not obvious. What's the formal charge for the aluminum?
Negative.
And what's the formal charge on the boron?
Also negative.
So they look pretty similar, but it turns out that one of them is a strong base and one's a weak base. We've just memorized that. Okay, yeah. So sodium borohydride is kind of the odd man out of this pattern. It's kind of similar to lithium aluminum hydride, but it doesn't, you just use slightly, it gives you the same product, but you use slightly different reagents. You can do it all in one step. Okay, so that turns out to come up in some aspects in the second semester, and in the first semester sometimes as well. So this is an important set of reagents. I think hopefully now we've clarified that. So what we're trying to do here is, I think we've made some good progress on drawing the products when you're, on predicting the arrows when you're given the starting materials. So we're starting to try to up the difficulty. We're starting to start learning how you can come up with the right starting materials on your own. And that's important because some of the hardest problems in organic chemistry are the synthesis problems, where you have to come up with the starting materials on your own. So we've started talking about how you can design an effective synthesis using Grignard reagents or alkyl lithiums or lithium aluminum hydride or sodium borohydride. All right, so let's go back to my screen. Let's see. So what are the patterns that we've seen? I think we've seen a common pattern is acid-base reaction, then nucleophile electrophile reaction, then an acid-base reaction.
Yeah.
Then another common pattern is sometimes we just do the nucleophile electrophile reaction first. Then we do an acid-base reaction. And another common pattern I think we've seen sometimes is this. I think this pretty much covers it. These are the three patterns that we've seen so far. Does that make sense?
Yeah.
Yeah. There is one complication. We've seen that actually, occasionally, the leaving group falls off on its own, and then you do the nucleophile electrophile reaction. So that is another complication. So things get a little complicated. But these are the three basic patterns. Do you notice what makes sense here is, so usually you do an acid-base reaction to give yourself a better nucleophile, or a better electrophile, or a better leaving group. Then you do the nucleophile electrophile reaction. And then what's the purpose of this step? The purpose of this step is usually just to get rid of the charge on the main molecule, right? So yeah. How do you know when you can stop here? You can stop here if there's no charge on the main molecule. But if you do the nucleophile electrophile reaction and there's still a charge on the main molecule, then you're going to fall into one of these two patterns.
Yeah.
Okay. And how do you know whether you're going to do this pattern or this pattern? Well, we know that if you have a strong acid, what's going to be the first step?
Acid base.
Good. What about if you have a strong base? Well, that's tricky. If you have a strong base, sometimes you just go straight into here and sometimes you go into here. It kind of depends on what strong base you're using. But we've been trying to learn about this. If you have these strong bases, what's going to happen first?
An acid-base reaction.
If you have these strong bases, well, you usually try to set up the reaction so that they're still going to act like nucleophiles. But if you mess up and you put in a protic solvent, then they're actually going to act like bases. Okay. And O- is tricky. O-, if there's an O-, O- can do either this pattern or this pattern. It depends on, you just have to learn the details of the specific reaction. So we haven't learned that very much. O- is very important in the course, but we haven't talked about it because it doesn't follow general rules. Okay, maybe we'll get into that in more detail later. So, all right, so I'm trying to summarize what we've talked about here so far. So O minus can go through either of these two patterns, or maybe this pattern, and you'll just have to learn the details as you go on. Do you notice anything that these three patterns have in common? The one thing they all have in common is that there was only one nucleophile-electrophile reaction. Right?
Yeah.
Sometimes two acid-base reactions, but only one nucleophile-electrophile reaction. These are the common patterns in the first semester. But in the second semester, there's many reactions that have two nucleophile-electrophile reactions. Notice that if you did it this way, you'd never have more than about 3 steps. But there's a lot of reactions in the second semester that have 6 steps, or something like that. So what's the pattern when there's 2 nucleophile-electrophile reactions? Well, that could look like this. This is the most general pattern. This is the most general pattern when there's 2 nucleophile-electrophile reactions. Notice that this kind of breaks what I told you before. I told you previously that you usually alternate. Acid-base, nucleophile-electrophile. Acid-base, nucleophile-electrophile. But this doesn't really fall... I can see that was actually an oversimplification. That doesn't really apply when there's 2 nucleophile-electrophile reactions. Then you kind of have 2 acid-base reactions in a row. Now, do you see how this makes sense? We would do an acid-base reaction to give ourselves a better nucleophile, or a better electrophile. Then we would do the nucleophile-electrophile reaction. Then we do an acid-base reaction to get rid of the charge. Then we do an acid-base reaction to give ourselves a new, better nucleophile, or a new, better electrophile. And then we do a new nucleophile-electrophile reaction, and then if there's still a charge, you do an acid-base reaction to get rid of that. All right, so this is a pattern we haven't seen, because all the reactions I've given you so far, there's only been one nucleophile-electrophile reaction. I just wanted to warn you that in the second semester, things start to get more complicated, and many of the reactions have 2 nucleophile-electrophile reactions. Here's another pattern. Sometimes you already have good nucleophiles and electrophiles at the start, so you don't need the first acid-base reaction. And here's another pattern. Sometimes after the nucleophile-electrophile reaction, the main molecule already has no charge. So then you don't need an acid-base reaction to get rid of the charge. So these are the common patterns. These are common patterns when there's 2 nucleophile-electrophile reactions. I hope this doesn't seem too confusing. It's a lot of text. But they're all kind of the same basic pattern. The key thing is, if there's going to be 2 nucleophile-electrophile reactions, they're usually separated by 2 acid-base reactions.
I see.
After you do a nucleophile-electrophile reaction, you usually need 2 acid-base reactions for the next nucleophile-electrophile reaction. This acid-base reaction gets rid of the charge from the previous step, and then this acid-base reaction prepares you for the next step by giving you a better nucleophile or electrophile. Okay, I'm actually not planning to do any specific examples of this with you right now. I just wanted to have this in your notes so that your notes are correct. I didn't want to give you the sense that all reactions in OChem are as simple as the ones we've seen so far. So what we've seen so far are these patterns. And that's what I'm going to keep working with you on for the time being. I'm not going to go over any specific examples of this with you, because these are better learned. These are better learned when you're just studying the specific reactions. But I'm hoping that you'll be accumulating all these notes and reviewing them in the weeks and months to come, so I don't want mistakes in the notes. So I'll just put this in your notes. Here's some additional patterns that we'll see later.
Okay.
But we're not going to go into that in more detail right now. I don't think this is the right time to go into it in more detail right now. We'll keep focusing on reactions with only one nucleophile-electrophile reaction. So this covers pretty much all the reactions in the first semester, and it covers a lot of the reactions in the second semester. But there's also a lot of second semester reactions where there's two nucleophile, electrophile reactions, and that's when you'll have to start learning these additional patterns. So we won't go into that in more detail right now, but we'll just say that that's an additional pattern, and we'll talk about it later. Okay, for the time being, we'll keep sticking with this pattern. So remember to complete the homework problems that you didn't get to this time. And then I'll probably send you another set of problems to work on. And I mentioned, remember as you're doing the homework to keep refreshing your memory of the tutoring session as well, and asking how are these homework problems testing what you saw in the tutoring session, because we covered a lot of material and it's easy to start forgetting stuff.
Yeah.
Okay, and so today we were kind of going over strong bases. They're a little bit tricky. We spent a lot of time talking about lithium aluminum hydride, Grignards, sodium borohydrides. That's some of the important stuff that we talked about there as well. And we've been focusing on these important patterns. So remember, when you did the homework assignment this time, there was a mistake that you were making on a lot of problems where you did this.
Yeah.
So that's something to watch out for. That is, you were not doing any nucleophile electrophile reaction. So remember, that doesn't match our patterns. After you do the acid-base reaction, then you should look for a nucleophile electrophile reaction. So that's something to keep in mind. Okay, all right. But overall, I still think we made quite a bit of progress, and we're starting to get to the point where you're able to predict what's going to happen even on reagents that you haven't seen before. So I think that's a very powerful tool for OChem.